All right, so now that we did a few examples of converting values from decimal to fixed point representation, let's talk a little bit about some of the properties of the fixed point representation. And let me give you a motivating example. Suppose that I have I have like an 8-digit value or a 4-digit value. So let's say 1, 2, 3, 4, 5, 6, 7, 8. Let's even keep it a little bit simpler so it gets the point across. So if I'm using an unsigned representation of 4 comma 0, this means that I can represent the numbers I can represent integer values and no fractions whatsoever, right? Because I'm not allocating any space for the fraction. So this allows me to report or represent integer values with no fractions. On the other hand, if I do an unsigned 0 comma 4, this will be dot 1, 2, 3, 4. This allows me to store fractions, but it does not allow me to store any integers. So there is a trade-off. Let me give you, again, this kind of trade-off, like what's happening here. So obviously in the first example on the top, I can go, my range will be from 0 to 15, right? Because the minimum value I can record here is 0, 0, 0, 0, and the maximum value is 1, 1, 1, 1. So I can go anywhere from 0 to 15, and I can count by 1. So I can count by like 1, meaning I can go from 0 to 1, 2, 3, 4. So I can't even go by halves. I can go like 1.5 to 2, 2.5, etc. On the other hand, this value, or the second example, I can, there is no magnitude, like my range is really small. So the range is really small here. But I can represent very small values. Actually, in fact, the smallest value I can represent in this representation is 1 over 2 to the power of 4. So I can represent 1 over, so I can count by 1/16 increments. So the range is small, but my resolution is higher, right? So the resolution is higher. So here I'm going to say my resolution is up, but the range is down. On the other hand, this one, the resolution is down, but the range is higher. So there's a trade-off. And the measurements that we do to kind of figure out what fixed point representation is good for what, there's a few properties. There's the precision, there is the resolution, accuracy, range, and dynamic range. Okay, so these are some properties that are used to kind of compare different fixed point representation to each other. So for example, if you need to know if a certain fixed point representation will give you enough range or will give you enough resolution for the measurements that you're trying to record, or the program requires, for example, like very, very, very small resolution. Maybe you care about 1/28th increments, even smaller. Maybe you need to know that your representation works for that requirement. The precision is essentially just the number of bits, the number of non-zero bits. The resolution is the smallest value that you can represent, smallest magnitude that you can represent, and then the accuracy is the magnitude of the maximum value, the difference between the true real value and its approximate representation. And then the range is the smallest. Obviously, the range is this difference between the smallest and then the largest value. And then the dynamic range is basically the absolute number of combinations that you can have in that representation. And this is just simply 2 to the power of the number of bits that you have. So let's take a look at an example. Assume that I have the signed representation of 9, 6. Let's do a couple of things here. What is the precision of this representation? Well, the precision is, like I said, it's the number of bits that you have. So this is equal to, I have 1 bit for the sign, plus 9 bits for the integer, plus 6 bits for the fraction. So this is 16 bits, which means that this precision is a 16-bit precision. The resolution is the smallest value I can represent. Well, what is the smallest value? Well, if you take a look here, I have 6 digits for the fraction. So the smallest value I can represent is 1 to the power of -6, or 1 over 2 to the power of 6, which is 0.0 0.015625, which is actually good, but again, depending on what the application is, this might not be good enough. The accuracy, you divide the resolution by half. The range will be the minimum value, which will be a negative sign, so the sign bit will be 1, and then the remaining bits are going to be equal to 0, and then the largest value will be when the sign bit is equal to 0 and the remaining bit, come on, are equal to 1. You take the difference, and that will give you the range, and then the dynamic range is basically the 2 to the number of bits that you have, so 2 to the power of 16, which is 64K, so 65536. Okay, so now again, if you want to compare this, for instance, to something else, let's say you want to compare it to unsigned 10.6, you do the same thing. The precision is 16, the resolution will be 1 over 2 to the power of 6, the range will be different, and the dynamic range will be the same. And these are the properties that, like I said, are usually used to measure how good a certain fixed point representation is good for the application intended. The last thing I will mention here is that if you're doing mathematical operation on fixed point representation, you need to be aware of the number of bits that are required for the result to be stored. And this is just like any mathematical kind of understanding. If you have, for example, if this helps, here we go. So let's say you have a 2-digit number and you're multiplying that with another 2-digit number, there is a chance that the result will actually be 4 digits, right? The maximum value will be 4 digits. So when you do fixed point representation, if you're adding numbers or you're multiplying numbers in fixed point representation, you just have to keep in mind that the number of bits must accommodate for the result. So for example, let's say I have an unsigned number of 4, 4, and I'm multiplying this with another number that is unsigned, 3, 3. The result actually must accommodate for the maximum number of digits I require to store the result. So that will be 7, 7. You add the number of bits for the integer and number of bits for the fraction. So I can give you an example, but I don't want to stretch this video to be very long. But you can do this multiplication on your own if you like. So let's say you want to multiply 0.00011.110 by 0.00010.100. This multiplication will take multiple, there's a bunch of steps, but there's a shortcut for it. Anyway, the result actually will be, come down here. 0, 0, 0, 1, 1, 0, 1, 0, 0, 1, 0, 0, 0, 0, 0, 0. Now, if you look at this, you'll see that the fraction actually turns out to be 6 bits, and then the integer part is actually 10 bits. And that's because we had 5 bits for the first integer and 5 bits for the second integer part. So 5 plus 5 is 10. So we needed this 10 bits for the result for the integer. And then we had 3 bits for the fraction here and 3 bits for the fraction here. Together will make 6 bits. So it's just something to keep in mind. Maybe this was a little bit too in details for our purpose. Nonetheless, it's something that's worth mentioning here. And then in the next video, we'll talk about floating point. Thank you for watching.